In the last lecture, we saw how important it was for the cardiovascular system to increase blood flow and oxygen delivery to the contracting muscle. That's only effective if the arterial blood is fully saturated, and that's the function of the respiratory system and forms the basis of this lecture. The important functions of the respiratory system during exercise are to maintain the arterial oxygen saturation, to facilitate the removal of CO2 from the contracting muscles, to contribute to acid-base balance, and it does that by blowing off CO2 and regulating the hydrogen ion concentration. And to a lesser extent, the respiratory system is involved in fluid and temperature balance. The air that is exhaled during exercise is humidified and is at body temperature, and so you can lose some fluid and heat from the respiratory system. The respiratory system achieves this by increasing both the minute and the alveolar ventilation. The minute ventilation is the total volume of air that's moved in and out of the lungs each minute, and is the product of the tidal volume, the volume of air in each breath, and the breathing frequency. Because not all of the airways are involved in gas exchange, and there is a dead space, the alveolar ventilation is really the effective ventilation of the lungs that leads to gas exchange. And this is the product of the tidal volume minus the dead space and the breathing frequency. There isn't much change at all in the anatomical dead space, but during exercise under certain conditions, there may be fluctuations in ventilation and perfusion such that the physiological dead space may alter slightly. If we look at the ventilatory response to exercise, again we can look at prolonged exercise at a given exercise intensity and incremental exercise, which we'll speak about in just a moment. And as you can see, at a given exercise intensity, there's an initial rapid increase in ventilation, followed by a slow upward movement in ventilation, largely due to a slow drift in breathing frequency, similar to the increase in heart rate that we see in the cardiovascular system over time. The rapid increase implies some involvement of neural control mechanisms, and the slower adjustments probably reflect a combination of neural and humoral modifications. The classic ventilatory response to incremental exercise has been the source of much study in exercise physiology over many years. And what you see here is the exponential rise in ventilation as you increase exercise intensity and the oxygen uptake. And as I said, there's been much debate about the mechanisms here. If you look at the pattern, you can see a fairly linear increase at the lower exercise intensities, and then a non-linear phase, and then a very sharp increase at higher exercise intensities. Now, as I said, this has been modelled as an exponential increase, and some have argued that it really is a continuous exponential function and shows no threshold phenomena. On the other hand, some investigators have argued that there are discrete thresholds that reflect various biological processes that contribute to ventilation. Notably, at the lower intensities, this first break here is being postulated to be due to the beginning of lactic acid production. And the buffering of that acid leads to an increase in CO2 that's derived from buffering rather than from metabolic processes within the muscle. Some have referred to this as the anaerobic threshold, and there's been much debate around that whole nomenclature and the underlying mechanisms. We won't spend a lot of time talking about that. Suffice to say, there's been much debate as to whether there truly is an anaerobic threshold during incremental exercise. At the higher exercise intensities, there are additional factors that stimulate ventilation over and above CO2 from either buffering or from metabolic production. And these factors we'll talk about a bit later, but they include increases in potassium, hydrogen ion, adrenaline, body temperature. Interestingly, during most of the low to moderate intensity exercise, this increase in ventilation occurs in the absence of any change in arterial oxygen content or partial pressure, or in the partial pressure of CO2. And in fact, at the higher exercise intensities, with hyperventilation, arterial CO2 levels actually decline. And again, that raises a lot of questions about the various factors that contribute to this increase in ventilation during exercise. The important function of the respiratory system is to oxygenate the pulmonary arterial blood so that the blood that returns to the left atrium is fully oxygenated and that can therefore be sent around to the rest of the body. And as you can see from this graph, pulmonary oxygen exchange and CO2 exchange occurs by diffusion in the lungs and therefore is critically dependent on the partial pressure difference between the alveolar gases and the blood gases passing through the pulmonary circulation. At rest, you can see that the mixed venous PO2 is about 40 millimeters of mercury, and it very rapidly equilibrates as it passes through the lungs up to alveolar oxygen, which is about 100 millimeters of mercury. During exercise, there's an increase in cardiac output and an increase in pulmonary blood flow, which reduces the transit time, but there's a drop in the mixed venous PO2 as the contracting muscles and other active tissues in the body consume oxygen. But you can see over time there's equilibration so that by the time the blood is leaving the lungs, it's fairly much fully oxygenated. Clearly then, if there are challenges to this, either by going to altitude, which would lower the inspired PO2, or if there are further increases in pulmonary blood flow such that the transit time decreases, then there is the risk of incomplete pulmonary gas exchange and some level of arterial desaturation. In most healthy people exercising at sea level, the arterial oxygen saturation and partial pressure is pretty well maintained, which is testimony to the effectiveness of the lungs in ensuring adequate pulmonary gas exchange, particularly in terms of oxygen. There are, however, some exceptions, and this was observed as long ago as the 60s, but systematically studied really from the 80s. And the observation that in some individuals during maximal exercise approaching the maximal oxygen uptake, they did show some level of arterial desaturation. And you can see there's some variability in this response, with some subjects showing no or only modest arterial desaturation, others showing a greater extent, and some showing quite significant arterial desaturation. The most likely cause of this is thought to be a pulmonary diffusion limitation, largely as a function of a large increase in cardiac output and pulmonary blood flow. This decreases the transit time and challenges the ability of the lungs to fully saturate the blood that's flowing through the pulmonary circulation. There may be some inequalities in the ventilation perfusion ratio, and it's also been suggested that there may be an expiratory flow limitation or a mechanical constraint which impedes a truly maximal ventilation. Whatever the cause, and as I said, most likely the pulmonary diffusion limitation is the most likely reason. This desaturation does have implications for locomotor muscle fatigue and exercise limitation because it can reduce the amount of oxygen that's delivered to the contracting limb skeletal muscles. During exercise, particularly at a high intensity, the respiratory muscles become very active and expiration may even become an active process involving recruitment of the expiratory muscles. Close to VO2 max, the respiratory muscles may account for as much as 15% of the oxygen consumption and cardiac output during this type of exercise. Although the diaphragm is well adapted for prolonged oxidative work and is relatively fatigue resistant, it's possible under certain circumstances that the diaphragm may fatigue. And at high intensities, this does result in a reduction in active muscle blood flow due to a reflex, and I'll talk about that in just a moment. There's been some investigation as to whether respiratory muscle training may provide some advantage, even in well-trained subjects, and there are a number of studies suggesting benefits of this type of respiratory muscle training for endurance exercise performance. As I said, during strenuous exercise, there is the potential for the diaphragm to fatigue. This is a somewhat complicated slide, but the important measure is really the transdiaphragmatic pressure, which is a measure of the ability of the diaphragm to change the intrathoracic pressures to facilitate airflow into the lungs. Before strenuous exercise, if you stimulate the phrenic nerves and measure the transdiaphragmatic pressure difference, you can see a reasonably high level here. If you repeat these experiments after strenuous exercise to fatigue at about 90 to 95% of the VO2 max, and then stimulate, you can see that the pressure developed is much less. And this reflects the reduced capacity of the diaphragm to generate this pressure following strenuous exercise. Note that it occurs at pretty high intensities. So for most submaximal intensities, the diaphragm is fairly resilient and fatigue resistant. Nevertheless, as you approach these high intensities, it has been shown that there is a reflex from the diaphragm through the circulation to limit the motor drive to the contracting muscles. And this is a good mechanism to try and preserve the function of the diaphragm and indeed preserve the oxygen availability for the brain during very strenuous exercise when oxygen supply may become limiting. There's been much discussion about the factors that contribute to this increased ventilation during exercise, or the hyperpnea of exercise. As we saw for the cardiovascular system, there is evidence of so-called central command, or activation in parallel with activation of the motor cortex. There's evidence that the type 3 and type 4 afferent fibres in skeletal muscle, which respond to various metabolites, can also influence the ventilatory response to exercise, and possibly the spindles or even the Golgi tendon organs, which respond to changes in length and tension within the muscle, might have some feedback into the respiratory centres and may explain some of the associations between pedalling frequency, limb movement, and ventilation during exercise. The ventilation during exercise is very closely linked to the carbon dioxide production and the CO2 flux to the lung. And given the relative constancy of arterial PCO2, this raises some interesting and perhaps challenging questions about how that CO2 flux to the lung is actually sensed. At higher exercise intensities, increases in plasma potassium, decreases in blood pH or increases in hydrogen ion, increases in lactate provide additional stimulation to ventilation, as do the elevations in plasma catecholamines, notably adrenaline, and also body temperature. The ventilatory response can be modulated by lung and chest wall mechanoreflexes, and as I mentioned earlier, as you approach maximal ventilation, you may reach the limits of the flow volume curve, particularly on expiration, and there may be this mechanical constraint to ventilation. And finally, there's no clear evidence of any role for oxygen or hypoxia in regulating the ventilatory response to exercise. If we look at what happens after training, one of the characteristic adaptations to training is a right shift in the ventilation workload or oxygen uptake curve. And you can see that the ventilation curve is shifted to the right after training. And you can see the changes in a number of parameters that have been suggested to affect ventilation during incremental exercise: the right shift in the lactate curve, a right shift in plasma potassium, and a slower development of acidosis during incremental exercise. Reduced activation of the muscle afferents, and generally exercise in the trained state feels a bit easier after exercise, and these are adaptations which contribute to improved exercise tolerance after training.